Like I just got back from the library and like he weren't in the room.
Yeah, a lot of people do it so
I haven't gotten a response.
Begin,
Should I go?
or rather continue, because
I don't know what to do.
we stopped in the middle of something last time. Representations of functions.
Respond.
Okay, start paying attention now. Start paying attention. So, I don't remember what order I put them in, but let's just go through them. We had 6 main ones. One was a mapping diagram. And you're not going to use these a lot, but it's basically where you draw the domain of a function and you draw the codomain of a function. And you actually map things across like so. And you really only use this to kind of come up with certain ideas for certain things or to illustrate ideas, but you don't really do it much. But it basically tells you how to visualize certain things happening. So if there's a function that you don't understand very well, you can sort of kind of draw it out, make the connections that you know, and you can kind of figure something out based on that. Now, it's one of those things where it's very elementary and you kind of do it for a few minutes in an algebra class or a pre-calc class and you never see it again, and then it comes time, then you go to another class like, where's yours? Then you go to another class like advanced calculus and you start dealing with these functions that you don't even know how to visualize, and you go back to the basics, draw a mapping diagram. Yeah, so that's a mapping diagram. Another way is the verbal description. So technically, whenever you are solving a word problem or something like that, you're using a verbal description. So let's say I want to actually make something a little bit more specific. So you can draw this under the old mapping diagram. Let's say I had some function where it takes 1 and it connects it to 2. It takes -1 and it also connects it to 2. It takes 2 and that connects to, say, 5. It takes 3, that connects to 10. It takes 0, that connects to 1, etc. I can also point out, maybe if it would help you, that there would be a -3 hovering out here, and no one is going to connect to that. How do you describe what I just described over there in words? Verbal description of this function. So remember, a function is just a rule that tells you how to make a certain kind of connection. What is the rule that I was thinking about when making these connections? Yeah. That's the definition of a function in general. That's true for every function. I'm talking about this specific one right here. What rule can you think of, if any, that connects 0 to 1, 1 to 2, -1 to 2, 2 to 5, 3 to 10? And it's never going to connect anything to -3. Can you think of any rules that would do that? What would you do with the input here? Do you see it? I'll just tell you, it's not really important for the lesson. Square it and add 1 is what I was doing. So this was the rule. Every time you give me someone an input, remember that's what we call the domain elements, I'm going to square it and add 1 to it. So 0 squared plus 1 is 1, 1 squared plus 1 is 2, -1 squared plus 1 is also 2, 2 squared plus 1 is 5, 3 squared plus 1 is 10, and if you take any real number and you square it and you add 1, you will never actually hit -3 if the codomain is also the real numbers. So the domain is the real numbers here and the codomain is the real numbers. And remember what we had, we said the range is the set of all outputs. So in this particular guy, the range is going to be all reals, and they would have to be greater than or equal to 1 in order to be an output of this particular rule. So that's a rule. Verbal descriptions also come in, say, word problems are an example. And one thing I want to mention about the verbal description of a function. Now, we tend not to like it because we tend to start out with the verbal description, then we want to get rid of it. Okay, let's translate these words into functions, into formulas, and actually do something with it, or translate it to a picture. But the understanding the verbal is important. In fact, that's kind of where all understanding stems from. So like I tell you, a lot of students, they focus when they're studying on reading the examples. You should be reading the verbal descriptions. What are the strategies? What are the definitions? What are the terms that we need to know? There are, you should know, to be able to understand them. That's short for mathematical translations. That's going to be super important. So there are some words, I'm not going to tell you all of them because at some point in your life you would have seen them. I just want you to make sure that you remember these things. So you might see the word sum, and you might see the word product. You might see the word off. You might see the word is. You might see the word percent, etc. What does sum mean? It means addition, right? So it means to add. Now, generally you could actually talk about a sum with subtractions in it because you can talk about adding a negative. Generally includes subtract as well. But usually if you say the word sum, people are going to think add. The word difference would actually mean that you're thinking specifically of a subtraction. So that would mean subtract. Product. What does product mean? It means multiply. The product of 2 and x is 2 times x. What does off mean? It also means multiply. What does is mean? Equal. What does percent mean? No?
No, I don't know.
See the word percent. What does it mean? Huh?
Like if you're taking a percent.
Yeah, but
That's right.
yeah, but it's a specific one though. Huh? Divided by 100 specifically. Right? Percent, word from century, 100. So these are, every now and then I'll have students who come to me with some kind of problem that they're having. Oh, I have trouble with percentage problems. And it's a very strange thing for me to hear because the word literally tells you how to solve the problem. Every now and then, you're going to be in a situation where the language of the problem literally tells you how to solve the problem. So for example, if someone were to ask, what is 25% of 17, right? And you can have a student who might, you guys probably wouldn't have trouble with this, but you can have a student who would have trouble with that kind of question. And the funny thing about that is, the question itself has the answer. If you literally just know what the words mean in the problem that you're reading and directly translate it, what? I don't know what. Call it something, a variable. X is equals 25. Well, that's just 25. Percent. Divide by 100. Off means multiply. 17 means 17. So x equals 25 divided by 100 times 17. The answer is hidden within the question itself. And this is going to happen a lot in mathematics. A lot of times students have trouble with things. It's not because of the math. It's because of the vocabulary. You don't know the words. You don't know the phrases. You don't know the strategies. You don't know the formulas. The better you can talk about math, you'll automatically be better at math just by knowing how to talk about it. So every now and then, I'll be seeing one of my students walking on campus, and I'll just stop them and ask them a question. Hey, how do you solve this equation? And I don't want a specific answer, I just want them to tell me in words how they would do it. Oh, well, first I would do this, blah, 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 blah. And the better you can do that, the better you will be at math automatically. If you just go through your notes and just learn how to talk about everything that's in your notes and never practice a problem, your grade will jump by 20%, 30%, 40% automatically. How do you solve an equation? Well, it's kind of like this. If you have to write down a specific example to explain to me what the thought process behind something is, it means you don't understand it. It means I'd be able to give you a test and trick you. That's what that means. Understand the words. Yeah, I solved a bunch of problems and I was doing okay. I know how to solve equations. What's an equation? Well, how do you solve an equation? If I give you a random equation, what's the first thing you would do? Well, suppose you gave me this one, right? I would do this. No, like in general, what is the first thing you think about when you want to solve an equation? Tell me in words. If you can't do that, then math will forever be hard to you. I don't understand what's going on. Okay. It starts with a verbal description. So I know we kind of gloss over math. The calculations is the sexy part. Everyone wants to know how to cancel stuff. No, learn how to talk about it first. It's a very important thing. And what you'll realize it's strange. But I used to work in tutoring centers all the time, and I can tell you, 30–40% of the time, a student would ask me a question about something they're confused about. I'm like, the answer is literally just what you just said. Take your question, translate everything. You have the answer right there. Right? So a lot of the times, overlooking the verbal is going to be a problem. Most students, they never pay attention to it, but it's a very important thing to pay attention to. So when you want to study, you do not start studying by doing a bunch of examples. You start by learning your vocabulary. That is where you start. What do we call this? How is it named? What is the notation? What is the strategy? That's where studying begins. And that actually directs your calculations. And that makes sure you know what you know. Because a lot of times, a student might be able to get through some example because they saw me do something similar in class. And so they tell themselves that they understand what's going on. Oh yeah, I really understood what was going on. Blah, blah, blah. No, you just knew how to do this particular example because I did something similar in class and you just mimicked me. That's not you understanding what to do. Like if I tweaked one little thing, now you're all messed up. And that happens because you don't have a language. It's not a math problem, that's a language problem. So the verbal description is very important. I don't want to harp too much on it because I want to get through a certain part of the lesson, but it's important. That's where your studying starts. And it kind of shows up on a test. So sometimes I see students, they're writing things and I'm like, where are you going with this? It's because they don't have an idea in normal language of what they should be doing. So I see an equation and I'm like, okay, the first step would be to get everything to one side and have 0. And yet I'd see the student like, there's 7 lines in and there still isn't a 0 on the other side. It just means they don't really know where they're going. They don't know how to express to themselves, here's what I should be doing. And that is going to be the root of all your problems, right? Understand the verbal, don't overlook it, it is very important. It is where you're that's the root of your understanding and everything grows from that. So another way to describe a function would be as a table of values. Or coordinates, mentioned this before. More specifically, a set of coordinates. So I could talk about the above example where I can tell you, okay, x was 1, the y is going to be 2, and if x is minus 1, the y is still 2, and if x is 0, the y is going to be 1, and if x is minus 3, the y is going to be 10, etc. So it can be described to you like that. In statistics is a lot of times how functions are expressed, because you can't have a formula for a lot of statistical phenomena. You don't know a rule that everything is following. Everything seems random to you at first, so what you do is you just plot a list of connections that you know about, and the goal is to figure out some order among the chaos, right? And that's where regression lines come in and all that kind of stuff. So sometimes you have to resort to doing that for representing a function. Doesn't happen often in calculus, but in general, this is going to be nice. Or you might name the function f and you just write it as a set of coordinates. So 1 connects to 2, and minus 1 connects to 2 as well, and then 2 would connect to 5. Right? And you can write it like that. So that's one way to express a function. And if you don't have a nice formula to talk about it, that is good enough for a lot of cases. The fourth way to express a function, graphing. This is when you draw the picture of the function. So thank God in the 1700s, the philosopher Descartes figured out a way that we can visualize almost quite literally what equations would look like had they have a picture. If they were to have a picture. So this particular one would look like that. That would be the picture. I'd be able to connect, I'll make all these connections. So the 1 would actually connect to the y value 2, and the 2 would actually connect to the value 5, and etc. Right? And I can actually plot all the possibilities here. 0 will actually be connected to 1, and etc. And then you can draw this picture, and that's you visualizing the function. You can actually draw a function. This is very useful in calculus. Or I'll say the calculus track. So algebra, pre-calculus, calc 1, calc 2, calc 3, calc 4. Although by the time you get to calc 4, you're drawing things in 3 dimensions, and it can get pretty sketchy, but quite literally sketchy. But being able to draw a picture is going to be very important. And one thing you can do is from the picture, the nice thing about pictures is that you can talk a lot about a function and its behavior pretty much at a glance without you needing to do too many calculations. So for example, I can say, for this particular function, the minimum value is going to be 1. I would know that no number that's negative will be an output of this function. I can understand that, oh, this function deals with the negative sides and the positive sides in exactly the same way. I would notice that negative 1 is doing the same thing as positive 1. Negative 2 is doing the same thing as positive 2, and etc. Such a function is called even. This is called an even function. So you can actually look at the picture and you can talk about the behavior of the function. And like I said, being able to talk about something is insanely useful. If you can draw a picture is worth 1,000 words, and the words are everything. Words are worth everything. Okay. So you can have the graphing, and I actually showed you how to graph a bunch of things already. 5. We have, well, the formulas. Was there another one I mentioned besides formulas? I feel like I mentioned 6 of them last time. Mapping diagrams, verbal descriptions, table of values. Oh, I split these in 2? Okay, so this is 3 and 4. They're very similar though. You just know that the part in the first part of the table goes in the first coordinate. The important thing is, for a function specifically, every element in the domain appears first in one coordinate. The moment this rule is broken, that list of coordinates you're looking at is no longer a function. So if I were to give you this list, and there's another point in this list where I tell you 1 also gives me 3, then the list you're looking at is no longer a function. And if I tell you, well, and if you notice that there's a coordinate that's like 0 was missing, there's no 0 blah, that's missing, also what I'm looking at is not a function. Every element in your input space must be mapping to something. That's what makes it a function. Everyone in the domain is connected to something. They're connected to only one thing. So every element in your domain must appear as the first number in one coordinate. The moment you don't have that fulfilled, you are not looking at a list of functions. There are other relationships that we care about, but this is the function relationship. And 5 is when we talk about algebraically. Now this is the sexy part. This is what everyone thinks math is all about. Right? You ask people what math is about, they'll tell you about calculations. This is a very short-sighted thing. It's not what math is about at all. This is just how we like to express our thoughts. But the thought pattern is much more important. So this is when we use formulas. And that's where we could write something like this. So that is how we can actually express our verbal description of the function in mathematical symbols and operations. And the main reason why this is nice is because it's more concise, and that's pretty much the only advantage. That's one of the main advantages. I guess there are a couple more. But you can express this as a formula, as an idea. And these guys, very useful in the calculus track. So normally when you're given any other description of a function, you're going to want to be able to either express it as a formula or express it as a graph, because what I'm teaching you teaches you how to manipulate those things. It's very hard, like we haven't taught you to manipulate the other things. There are other classes that teaches you how to actually manipulate the other things. Useful in the calculus track. So we'll tend to want to change other descriptions to type 4 or 5. Okay? And that's where calculus and algebra really shines. Once you can give me a formula or picture, that's where I can do stuff with it. Now that we know that that's where we want to live, we actually spoke about graphing a little bit. When you want to graph, what's the first thing you do? Huh? No? Find the x-intercepts is the first step. Okay. I come to your, wake up at 4 a.m. in the morning. What's the first thing you want to do in draw a graph? You just like, x-intercept, x-intercept, find the x-intercept. How do you find the x-intercept? Okay. Set y equals 0, solve for x. You're supposed to be able to immediately respond. The moment you can't immediately respond to something like that, that's what should concern you. The fact that you can get through a few examples on the practice test, irrelevant. Largely irrelevant. If I can ask you what to do and you can respond to me, okay, I know you're going to do fine. Let's talk about combining functions. Sometimes we want to actually combine these rules together. Functions, each function can be doing its own thing, but when you put them together, you want to be able to accomplish something by putting them together. So we can combine functions. So I can have two functions, f and g. With the same domain. We define f plus g. You can write this expression. That just means you add the formulas. So this means the formulas. This represents the formula description. And you can create the function f minus g. That's just you subtract the formulas, where, especially if there are several terms, you would want parentheses around this. You can multiply the formulas, fg. And generally speaking, you'd actually want parentheses around both. You can divide formulas, f over g. And of course here we would require that g is not 0, because you can't divide by 0. There's another very important way to combine functions that is called the composition. I want to deal with that separately though. Let's actually just do some examples here, even though, yes, I know we all know how to do it, but let's actually just do it. So, basically now what we're going to do is we're going to take it way back. Back in the day when we were talking about combining like terms and all that stuff. That's how we're going to do this. Back to the distributive law, what it means to combine like terms. How do you add two things together? How do you subtract two things? I've actually painfully described this before. I had people rolling their eyes at me. I know that. Everybody always knows until the test comes, and then they're like, I don't know what happened. Like before the, yeah, I know that, I know that. Test. I don't know what happened. Okay. So, A, let's talk about F plus G. This literally means you take F, you add G. In general, you don't need parentheses here. You just write down one verbal description plus the second verbal description. How do you deal with that? Well, this, like I said, goes back to the basics. We can combine things by adding like terms. So I find out where all the x squares are, I combine them. So I write down the like term once, and then I add the guys on the outside here and write that as the coefficient. So there are two x squares. Technically what I did was I factored. It's like I had an x squared and an x squared, and I can factor out an x squared. I'd be left over with a 1 plus 1, which is the 2. So that's technically what's going on, but most people don't think of that. But that's what's going on. You're actually just combining things and factoring out the like terms. So you can combine the x squares. There's only one 5x, so nothing to combine that with. The 4 and the minus 4 and the 6 are also like terms. You combine those to get 2. If I talk about the subtraction, then I'd write down the first formula description. I would write down a minus sign. I would write down the second formula description. I will be sure to put in parentheses here because distributive law will take effect. And we now have the x squared minus the x squared, and there are no x squares, then I just have a 5x and plus 10. So that was the answer here. That was the answer here. We can move on to C. F times G. I don't want to write the dot because that might confuse you with the other notation. And this just means I write down one verbal description. I write down the other verbal description. I put both in parentheses separately, and then I apply the distributive law. So how would that be applied here? What do you do? How do you describe distributive law? Right, you take each term here, multiply each term there, and then you combine like terms at the end. Now, in taking each term and multiplying out each term, the laws of exponents will take effect. So I'm going to take the x squared, multiply these two. So that would be x to the 4th minus 4x squared. Then I'm going to take the 5x, multiply those two. That's going to be 5x cubed minus 20x. Then I'm going to take the 6, multiply everybody. That's going to be plus 6x squared minus 24. Now you combine the like terms. So there's only one x to the 4th, so that's that guy. In terms of x squares, there's a minus 4x squared and a plus 6x squared, so that goes to plus 2x squared. In terms of x's, come again?
5x, 5x.
Yeah, the squares, we have the 2x squared, and we just put in the x to the 3rd. Then I have the x's, there's only one of those, minus 20x. And as far as numbers go, there's only one of those, minus 24. The order doesn't necessarily matter, but yes, there's a nice thing to being able to have the powers descending. So we can have that, and we can have did add, subtract, multiply, divide. Write one verbal description over the other. Now, we're going to do division of polynomials pretty soon. I don't know if we'll start by the end of this lecture, but definitely by the next lecture, we're going to talk about dividing polynomials in general, especially when they don't actually nicely factor and cancel. So now you know that is the function, you just put one over the other. You also know that x cannot be minus 2, and your x cannot be 2, because that would make the denominator 0. Now this will apply. Now you may simplify. Do these guys factor?
Yes.
And here's the thing that people always forget about simplifying. So I could simplify this. And I would get x plus 3 over x minus 2. Now the reason why there were certain situations in which I told you don't simplify this, combine everything in big fractions, is because simplifying does not fix the domain. And this is a very, very important thing for you to know. So, if you look at the formula description for this, it would seem to you that I'm allowed to plug in minus 2, because if I plug in x equals minus 2, there's no problem. However, this wasn't the original form of the function, that was. I would still need to restrict both minus 2 and 2 from this form, because I have to remember where it came from. Both of those couldn't work in the original, they will not work in the simplified form. So that leads to a very important idea. Simplifying does not fix domains. It just makes it easier for you to digest and apply your mathematical principles, but it doesn't actually change anything. And this actually came up, I mean, technically the way it came up, there are other ways for you to know that that had to work out. But there was the homework problem where, and I think I mentioned this for another reason before, but where it gave you like an even number here, and then it was v to another even number here, and let's put the smaller one here just to look nice, 8 and 24. And most people simplified that to be v cubed, and they swore they did the right thing, but the thing is, these two had different domains. They were fundamentally different functions because they had different outputs. And there was a rule that I told you that whenever the number here is even and the power is even, it actually translates to the absolute value. So the actual correct answer was that. But besides the point, you have to understand that when you simplify something, it doesn't fix the issues that were previously there. So the issues are going to be there even though technically you can't see them. And that's very important for you to know mathematically. And you'll also know that if you have a calculator like a TI-89 that can remember things, you're not going to fool your calculator. Like you could actually type that in there and your calculator is going to give you all the right outputs all the time. It's going to know, yeah, I simplified this to print it out on screen, but I know originally this couldn't work. It's not going to work even after simplification. That's something important. We will talk about dividing polynomials in more detail because that's going to be something very important. I was doing that with my Cal 2 kids just the other day because in order to solve certain problems, we have to simplify things by dividing out polynomials. We'll get to that. Another important way called the composition. So here's what a composition is, as well as why we like them. So let f and G the functions we define the function and it's called f composed with G. Or it's called f of G by, the notation is f, you put a little circle. So that's how we'd write it down informally. You want to be very, you'd write it f of G of x. And basically how we define that function is that we take the outputs of the function G and we use those as inputs in the function f. Right? Now why that's nice is because it allows us to string functions together in a very efficient way. So here you might have the domain of G, and here you will have the codomain of G. But at the same time, we can think of that as the domain of some other function. And then we can talk about the codomain of that function. So G is going to take some value. It is going to output some number, some other value called G of x. So G is going to do that. And then basically what it does is it passes the buck to f. F is going to take that value and it will output some other value, which is f of G of x. So you have functions passing things to other functions. This is called composition. We're composing the functions together. Kind of like when you're stringing an orchestra together, the guy's composing. Oh, you have the violin players over here and the trumpet players over there. You string them all together and something beautiful emerges. This beautiful thing that emerges is called the composition of the function. Okay? And by the way, this can go on for a long time. So we can have a bunch of little functions doing their own thing. Oh, one function does this to that, then another function does this to that, then another does this to that, then another does this to that, then another. Instead of talking about like 50 functions, I can talk about the one that brings it all the way from here to all the way there. In one nice little concise description of this entire process. This is what function composition is for. It's a very useful thing. And that's the notation for it. You put a little circle. It is read f of G or f composed with G. This is when you take one function, you plug it inside of another function. Now, to understand this, we need to understand evaluating functions. And to evaluate a function, what does that mean? At a specific input value is to compute the corresponding output value. FYI, this is just a language thing that I will mention because it'll show up, and if you don't know this, you can get in trouble. If someone mentions the value of a function without any context, they're referring to the output value specifically. So if someone is talking about the input values of a function, they'll specifically say the input values. or the domain elements, or blah. If someone just said the value of a function, they're always talking about the output value of the function. So if you're reading and there's someone talking, oh, the function values are blah, 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 they're talking about the y values, the output values. So that's going to be important for, like I said, vocabulary and understanding the language. Now, here's how you want to think about the formula. Here's how to think about the formula description. Say x is the independent variable. I believe I also described that last time. So the input variable is also called the independent variable. And y, which we might call f of x, is the output or dependent variable. Now, I'm going to talk about something that, despite the fact that it might look very simple, I want you to think deeply about this thing, because most people misunderstand, even though it'll look very simple when I describe it. So here's the important nugget of information, which will save you so much headache if you just know this one little thing. The x is a placeholder. Whenever you see a function formula, you do not want to think about it as some description of x. You want to think of it as a general description where x is just telling you where you can put anything you want. So, when I write, if I write f of x equals x cubed plus 2x squared minus 3, what you should be thinking when you read that is, here's a function that tells me how to do with blah. What I'm going to do is I'm going to take blah and cube it. I'm going to take 2 times blah, square the blah, and minus that. You want to think of the x as telling you a void, where if you put anything here, it shows up in this position and that position. That's it. That's how you want to think about a formula. A lot of people don't understand that simple idea. And it looks very simple when I write it down. But I can tell you from grading a lot of tests, most people tend to mess up on that idea. But this is how you want to think about a formula. When someone writes this down, there's a void here, there's a void here. That's how you want to see it. Right? X marks the spot where you can put anything in. And so you can write anything else here. So if you want to find f of 2, well, that means you're going to take 2 cubed, you're going to take 2 times 2 squared, and you're going to subtract 3. If I ask you what is f of a, you're going to take a cubed, you're going to take 2 times a squared, and do that. If I ask you what is f of x plus h, it means you're going to take x plus h cubed, 2 times x plus h squared, minus 3. Whatever I put in here is going to show up in these positions. Don't think of the x's as x's. Think of them as these are positions that you can put something into. Okay? And it's a very common mistake. It happens all the time whenever we're like computing a difference quotient. Right? So I ask for f of x plus h minus f of x all over h. It is very common for someone to be able to tell me, oh, this is x cubed plus 2x squared minus 3 plus h. And why they do that is because they don't understand that idea. They think of the plus h as something separate. No, whatever is in parentheses goes in all the positions that you saw x in before. You're going to actually remove all the x's and open up parentheses, and whatever someone writes here, you write it in all those positions. I'd also often see people writing the f on this side as well. Like, no, that's not what it means, so this is wrong. Okay, but it happens all the time. It happens even after I point it out to people. So it's something that you really want to pay attention to. Make sure you do not fall into that trap. It's going to be very natural for you to just think of adding an h at the end or whatever, but do not think of it. That's not how formulas work. So let's do some examples to make sure we get used to it, and hopefully we can get through these pretty quickly. to exponentials and logarithms. So excited. So I think we're going to do those next week. And then trig functions. I'm excited for that. Example 1. Let f of x equals 2x squared plus 3x plus 1. Let g of x equals 2x plus 1. Find f of g, g of f, g of x, f of g of 1. Let's start with that example. Okay, what would f of g mean? Well, basically, it means I'm going to take f, and as the input, I'm going to take g. Now, what does it mean when I see this? Well, because I'm thinking of f as a placeholder, whenever I see f, I automatically think there's a 2 and a void, there's a 3 and a void, and now what I'm doing is, inside those voids, I am writing g's. Which means there's going to be a 2 and something squared, 3 and something. And inside I'm going to write 2x plus 1 as that something. That's how formulas work. And at this point, we take it way back, we learn about distributive law, combining like terms, all of that starts to take effect now, right? The math builds on itself. And so now, you have to remember PEMDAS, so we're going to leave the 2, we're going to first deal with the powers, and that's going to give us 4x squared plus 4x plus 1, because the formula we FOIL out. This we can actually start to distribute at this point, 6x plus 3 plus 1. And here I can distribute this, so this is 8x squared plus 8x plus 8 plus those plus 6x plus 3 plus 1. And now you combine all the like terms, so that's the 8x squared, the x's, we have 8x and 6x, so that will give you 14x. And then we just have all these numbers, the 2 plus the 3 plus the 1, and that's 6. So that's going to be the answer. Now, technically speaking, you don't have to write down these 2 lines, but if you're ever one of those people who you often mess up when it comes to evaluating functions or difference quotients or anything like that, probably want to start practicing writing down these 2 lines until you really internalize that idea. But that's how compositions work. The formulas, the x's are just voids. When I think of f now, I'm just thinking of 2 void squared plus 3 times the void plus 1, and I drop things into the void as is described or as is needed. So that's how we would do f of g. Do g of f, it's the same idea. Well, this just means g and I put f inside of it. That means I'm going to have 2 times the f plus 1. That means I'm going to have 2 times, now I put in the f description. Now, we're back to basics, applying distributive law, combining like terms. How do I find this? Yeah?
Me?
What?
Me? Okay, 2 times 2x plus 1 squared plus 3 times 2x plus 1 plus 1.
Right. In fact, it's actually exactly the same as A. Right? Alvin was looking at me like, am I crazy?
Yeah.
He had that look. You know, he's like, wait, I feel like we've been here before. Am I crazy? Yeah, it's the same as A. I just wanted an excuse to point out that these two notations mean the same thing, because sometimes people see one and they confuse themselves. When you see this description, it doesn't mean multiplication, right? So if you mean multiplication, you would actually put the x here and then put the g of x. You'll see the of x twice. Once you only see one of them, and there's like a circle in the middle, or maybe even parentheses around here, that's composition. So you have to know how you're reading things. So I just wanted to point out, yeah, C and A exactly the same. No difference in how you actually deal with it. In fact, when I was doing A, I rewrote this as that in order to do it. What about f of g of 1? What does that mean?
You plug 1 into g of x.
You plug 1 into g of x? Yeah, so we actually have a couple ways to deal with that. Let's hope I remember these functions. Now, 2 ways to do this, 2 ways. So the main way, first, find g of 1, then plug that into f. So, we had your g of x is 2x plus 1. This means that your g of 1 is going to be 2 times 1 plus 1, because my x is just a placeholder. So that is 3. And so this means that my f of g of 1 is f of g of 1. Well, that just means f of 3, because I computed that was 3. But that just means it was 2 times something squared times 3 times something plus, was it plus 1? I forgot what one. 2x squared plus 3x plus 1. Right, and now I'm just going to put 3 in that position. And that gives you what? Huh? 25. So that's 9 times 2 is 18 plus 9.
Oh, yeah.
So that's one way you can deal with it. The other way is to first find the f of g of x and then plug it in. Or you might be in a situation where you already found f of g of x previously, as we did. First find f of g of x, like a general description for that rule. Then plug in 1. So we have our f of g of x, and this was going to be the 2 times the 2x plus 1 squared plus the 3 times the 2x plus 1 plus 1. We simplified that. What did it simplify to? It was 8x squared plus 14x plus 6. And so now this means that your f of g of 1 is going to be you plugging in 1 into this thing. So that's going to give you 8 plus 14 plus 6, and you'll notice that that's also 28. So you have a couple of ways you can do it. You can first find this part and then plug into that. Or you can find a general description of the composition and then plug a number into that. You have options. If it's just like a one-off kind of thing, then I probably go with the first option. But if I know f and g are functions that I'm going to be consistently working with, it might be worth my time to just find the general description, so I know whenever in the future I see f of g, I know how to actually talk about it in a shorter way, as opposed to having a two-stage process. So yeah, kind of depends on context which one you want to do, and so it's either by your preference. Personally, I find like for a one-off calculation, I'll probably do the method 1. for something that I know I'm going to be reusing these functions all the time, I'd like to have general descriptions of them just off the bat and use them at will any point later on. Now, let's compute some difference quotients. So you've seen this many times before. It is going to be something that, as I did on the first test, after a while, everyone's just going to expect you to know when you hear the phrase difference quotient, you know exactly what formula they're talking about. For f of x, so that's just some functions. It's difference quotient is f of x plus h minus f of x all over h. It's a very important expression. It's responsible for half of calculus, actually. So the first 2/3 of your calculus class is going to be focused on the difference quotient and how we can use limits, something called limits, to talk about the difference quotient. So one thing I want you to notice here is, let's say you have a function. This is your f of x. Then, if at one position, that's position x, so the actual output is going to be f of x. And if you have another position a little bit farther along the line, like just at a distance h, and you were to plug in that would be f of x plus h. You'd have these two coordinates. And here's something pretty cool. If you were to actually connect those two coordinates with a straight line, that line can be thought of as the average rate of change, the slope of that. We'll talk about that. This straight line represents what's happening on average. And that's going to be important for us to know a lot of times. So in between, your function can do whatever it was doing, but at the end of the day, it increased from this value to that value, right? And the line just tells you approximately what's going on between those 2 points. And so what you'll notice is that the slope of this is going to be, well, if I call this x1, that x2, this would be y1, that y2. That's going to be y2 minus y1, you have to know that formula, x2 minus x1. That's going to be f of x plus h minus f of x over x plus h minus x. X is what of course cancel, and you end up with this formula here, f of x plus h minus f of x all over h. So this description, the difference quotient, is really just a way to talk about the slope of some function between 2 points, x and x plus h. Sometimes we can talk about the a change in notation. So same function, same context, except we call the first position A, and we might call the second position B. So this would be f of A, and this would be f of B. And then we'll talk about the line over here, and then we'll measure the slope. And using y2 minus y1, it will be f of B minus f of A over B minus A. So that's just another way to talk about the difference quotient. It is equivalent. Now, because we know that slope is basically rise over run, we can actually describe how much a function is changing by looking at that slope, at least on average. So let's say I started out so let's say I have a function is doing as it do, whatever it wants to do. Let's say at one point, this is at, let's say 1, and this is 3. And then over here, let's say some units away, I'm at 5. And I realize over here, I am now at, let's say, 21. Notice if I measure the slope of this line, what would happen? The slope is going to be what? Well, 21 minus 3 over 5 minus 1, right? What would that actually give you? It's what?
4.5.
4.5. Now, what does that number mean? How can you look at that number 4.5?
Slope's increasing.
Slope is increasing, but more specifically, how we can look at this, one interpretation. It's an important interpretation. It's the interpretation that I want to introduce just now. For every 1 unit increase in x, the y increases by 4.5 units. And hence, the difference quotient is used to measure something that we call the average rate of change of a function. On some interval. So basically that 4.5 is telling me how the value of the function is changing on average on this interval between 1 and 5. On average, over this interval, the function is increasing by 4.5 units for every 1 unit increase. Now, it doesn't have to specifically be doing that at every single location, but overall, if I realize that I actually moved 18 units, if I realize that in the x I actually moved 4 units, then I know for every one of those units, I would actually increase by 4.5 units. So the difference in this is going to be 4, the difference is that is going to be 4.5 times that. So that's called the average rate of change. So whenever you see that phrase, that's also referring to the difference quotient. That's not the interpretation that makes calculus. It turns out when you interpret the slope in another very specific way, that's calculus. That's what calculus is about. So slopes are very nice. You can interpret them in a lot of different ways. So with that being said, I'm going to write down some examples and we'll breeze through them next time. And usually for average rate of change, the second formula is the one we like. With this interpretation, we usually use the f of b minus f of a over b minus a. We'll stop there. It's a little bit longer than I thought, but that's some very important ideas. Make sure you know how to think about functions, what a difference quotient is, and how to evaluate functions. All very important ideas.